The nucleus, part 4. Today we're going to talk about the density of the nucleus. The density of the nucleus is given by ρ equals to the mass of the nucleus divided by the volume of the nucleus. The mass of the nucleus divided by the volume of the nucleus. But if you want to calculate this density in an approximate manner, the nucleus is formed of protons and neutrons. Formed of protons and neutrons. The mass of a proton is 1.67 times 10 exponent minus 27 kilograms, approximately. The mass of a neutron is approximately 1.67 times 10 exponent minus 27 kilograms. We notice that the mass of a proton is approximately equal to that of a neutron, 1.67 times 10 exponent minus 27 kilograms. The nucleus is formed of protons and neutrons. The number of protons and neutrons in the nucleus is A. We say A nucleons. The nucleons are the protons and the neutrons. The mass of a nucleon, a proton or a neutron, is 1.67 times 10 exponent minus 27 kilograms. Let's denote by m0 the mass of one nucleon. The approximate mass of the nucleus is equal to A times m0. This is the approximate value of the mass of a nucleus. On the other hand, we can determine the mass of a nucleus by knowing the number of its nucleons A. On the other hand, the volume of a nucleus is equal to A multiplied by the volume of one nucleon V0. We obtain A times V0. V0 is the volume of a nucleon. A nucleon is assumed to be a sphere of radius r0. Its volume is 4 over 3 pi r0 cubed. The mass is A times m0. We simplify by A, we get m0 over V0. m0 is equal to 1.67 times 10 exponent minus 27 kilograms. V0 is 4 over 3 pi r0 cubed. r0 equals to 1.2 times 10 exponent minus 15 meters, or 1.2 Fermi. The result is 2.3 times 10 exponent 17 kilograms per meter cube. The density of a nucleus is 2.3 times 10 exponent 17 kilograms per meter cube. This number is very huge. In each cubic meter, what is a meter cube? It is a cube of 1 meter in length, 1 meter in width, 1 meter in height. If we fill it with the nuclei only, its mass will be 2.3 times 10 exponent 17 kilograms. In 1 cubic meter, we find 2.3 times 10 exponent 8 times 10 exponent 9 kilograms. This equals to 2.3 times 10 exponent 5 times 10 exponent 9 tons. We divide by 1000 when converting from kilogram to ton. Over 1 meter cube, when filling a volume of 1 meter cube, that is to say of length 1 meter, a width of 1 meter, and a height of 1 meter, by nuclei only, the total mass of the nuclei in the cube will be 230,000 billion tons. This is a very, very huge number. Let's solve an application to know the difference between the density of a nucleus and the density of an atom. Consider the nucleus of lead 208, whose mass is approximately 208 U. The atomic radius of lead 208 is approximately 280 picometer. The picometer is 10 exponent minus 12 meters. 1 U equals to 1.66 times 10 exponent minus 27 kilograms. R0 is the radius of one nucleon, 1.2 Fermi. The mass of an electron is 5.5 times 10 exponent minus 4 U. In the first question, we have to calculate the radius of the lead 208 nucleus. We calculate the radius of the nucleus lead 208. We use the formula R equals to R0 times A exponent 1 over 3. R0 is 1.2 Fermi multiplied by A, which is 208 exponent 1 over 3. The result is approximately 7.11 Fermi. This is the radius of the lead 208 nucleus. In part B, deduce the density of the nucleus. The density of the nucleus equals to the mass of the nucleus divided by its volume. The mass of the nucleus is 208 U. We use this conversion to convert it into kilograms. The nucleus is assumed to be a sphere. The volume of a sphere is 4 over 3 pi r cubed. This is the mass of the nucleus divided by the volume of a sphere of radius 7.11 Fermi. The mass of the nucleus is 208 U. We convert it to kilograms, multiply it by 1.66 times 10 exponent minus 27. The result becomes in kilograms. Here 4 over 3 pi r cubed 7.11 multiplied by 10 exponent minus 15 cubed. The result becomes 2.3 times 10 exponent 17 kilograms per meter cube. This is the density of the nucleus. The densities of all nuclei are the same. It doesn't matter which one in particular. They are always equal to 2.3 times 10 exponent 17 kilogram per meter cubed. Part 2a. Calculate the mass of the lead 208 atom. The atom is formed of a nucleus and its orbital electrons. Hence, the mass m of the atom is the mass of its nucleus, that is 208 U, plus the mass of its electrons. We have the mass of an electron. How many electrons do we have in this atom? The number of electrons in an atom is equal to the number of protons, since the atom is neutral. So we add it to the mass of its electrons, which is the number of the electrons Z multiplied by the mass of one electron. 208 U plus the number of protons, which is 82, multiplied by the mass of an electron, which is 5.5 times 10 exponent minus 4 U. The answer is 208.045 U. What do you notice? You notice that the mass of the atom is approximately equal to the mass of its nucleus. The mass of these electrons is approximately 0.045 U. This mass is negligible compared to 208, so we can consider that the mass of the atom is approximately 208 U. The mass of the atom reduces to the mass of its nucleus. This is always the case, since the mass of the electron is negligible compared to the nucleus. In part B, deduce the density of the atom. Repeat the formula above, but for the atom. It's the mass of the atom divided by the volume of the atom. We have the mass of the atom, the volume of the atom, which is assumed spherical, of radius 180 picometer, 4/3 pi r cubed. The atom is a sphere of radius r, 4/3 pi r cubed. (208 U), convert U to kilograms, multiply by 1.66 times 10 exponent minus 27. Now this becomes in kilograms, over 4/3 pi multiplied by r. R is 180 times 10 exponent minus 12. Each picometer is 10 exponent minus 12 meters. The density equals to 14,134 kilograms per meter cubed. This is the density of the atom. (14,134 kilograms per meter cubed). In the final part, we have to compare the nuclear density to the atomic density for lead 208. We want to compare the density of the nucleus to the density of the atom. When comparing two values, we say greater than, less than, equal to, etc. But here the density of the nucleus is much bigger than the density of its atom. We prefer that we find the ratio of their densities to know by how many times is this greater than this. Rho of the nucleus over rho of the atom. If we divide this by this, we obtain 1.6 times 10 exponent 13. or 16,000 times 10 exponent 9, or in other words 16,000 billion. Hence, the density of the nucleus is 16,000 billion times greater than the density of its atom. This is an extraordinary result. How can we explain this? This atom has a radius of 180 picometer. Or 180 times 10 exponent minus 12 meters. The radius of its nucleus is R equals to 7.11 Fermi, or times 10 exponent minus 15 meters. We notice that this radius is 1,000 times less than this radius, or several thousand times. Then the dimensions of the nucleus compared to its atom are extremely small, in the order of the thousands. So the dimensions of the nucleus compared to its atom is reduced to that of a point. This is the nucleus as a point. This is the atom. This is its volume. Its volume is much greater than that of the nucleus. But the mass of this atom is equal to the mass of its nucleus, but its volume is much greater than the volume of its nucleus. But the two masses are approximately equal. So, for the same mass, we have different volumes. The volume of this is much greater than this. In this case, m over v is much smaller than this m over v, since v here is much greater than v here. If you consider a certain volume, v, and we fill it with atoms, one next to the other. This is the atom and this is its nucleus. The point represents the nucleus. We notice that its volume V occupied by 8 atoms. If we want to fill the same volume V by as many nuclei as we can, we notice that we fill it by a much larger number of nuclei. So the mass here, M2, for example, this is M1, M2 is much greater than M1. Hence, this substance is much denser than the other substance. This is due to the volume difference between the atoms and the nuclei. The atom and the nucleus have the same mass, but the volume of this nucleus is much smaller than the volume of this atom. The mass here, the mass of the nuclei that occupy the same volume V, is infinitely larger than the mass of the atoms that occupy the same volume. And as a result, the density of the matter here is greater than that there. So the density here is much greater than the density here.